Here we are in part 2 of global change. In this part, we're going to focus on climate change. So here we go. First, before we talk about climate change, we need to really understand what the greenhouse effect is. And so basically what the greenhouse effect is the Earth is like a big greenhouse, hence the name, right? The atmosphere acts as the glass in a greenhouse. So the sunlight comes through the atmosphere, strikes the Earth's surface, and that surface absorbs that sunlight and warms the Earth, like the actual surface. And then some of that is reflected back into space as infrared radiation, aka heat. And so some passes through the atmosphere back out into space, and some actually gets absorbed and re-emitted by greenhouse gases. And so we'll talk about what your greenhouse gases are in just a moment. But this is actually really, really important. The greenhouse effect is pivotal for life on Earth. Without the greenhouse effect, the average temperature would be about negative 18 degrees Celsius. Basically, we would have no life on Earth without it. And so, the greenhouse effect is actually a really good thing, as are these greenhouse gases that cause it. And so greenhouse gases include carbon dioxide. And so carbon dioxide is really the gas that we measure everything else off of. So we say that it has a warming potential of 1. And so all of the greenhouse gases we measure off of carbon dioxide in relation to it. How much of a warming potential is it? And so carbon dioxide is what we base everything off of. And then next up we have methane. As you can see, it has a warming potential of 25 times more than carbon dioxide. Nitrous oxide is 300 times more than carbon dioxide. Water vapor has a very, very short residence time in the troposphere, and also has a very low warming potential, so less than 1, less than carbon dioxide. We don't really worry about water vapor so much because it's just the water cycle. It cycles in and out of the atmosphere so fast. Of course, there are anthropogenic greenhouse gases, including chlorofluorocarbons, which we learned about in stratospheric ozone depletion. But this is when the CFCs are actually in the troposphere, they act as greenhouse gases. When they're in the stratosphere, they act as or they deplete ozone. Speaking of ozone, tropospheric ozone is another greenhouse gas. So there's like a whole list of greenhouse gases, but the big 4 that you should really know: carbon dioxide, methane, nitrous oxide, water vapor. Remember, when we're talking about the greenhouse effect, we're talking about it in the troposphere, right? At the ground level. So keep that in mind as we're talking about that. A lot of people get confused with stratospheric ozone and greenhouse effect and climate change and global warming. They are different. They are not related because the stratosphere is ozone depletion, and in the troposphere is global warming and the greenhouse effect. So different things. Okay. So what happens when the greenhouse effect actually starts to increase because of excess greenhouse gases? And so more greenhouse gases we have, the less heat that escapes into the atmosphere, the more heat actually gets re-emitted back down to Earth. And so what this leads to is global warming. And so remember that global warming is actually an average global temperature. So if I were to average every single place on Earth together, you would get your global average temperature. And so global average temperature has increased approximately 1 degree centigrade since the 1800s. Who cares? 1 degree centigrade, 1.8 degrees Fahrenheit. Like, that's not a big deal, but it actually is, because it's not even across the Earth. It is actually different. Some places are cooler, some places are hotter, and as you can see in the GIF below, right, the places that are the hottest now, at least in 2013, where this graphic goes to, the Arctic is having a really, really hot time. And so the Arctic is a very large concern when we talk about global warming. So how do we know that it has risen 1 degree centigrade since 1880? Well, we can actually date the Earth's carbon dioxide levels and the temperature of the Earth through ice cores and sediments, and so we'll talk about that. Basically, though, right, we can see there are these periods of cooling and warming and cooling and warming all across the years. We can date back to 800,000 years ago, and so it has never been this high before in the last 800,000 years, and that's saying a lot. So how do we know that these temperatures are actually accurate? And carbon dioxide levels, right? So like I said, we can do dating and atmospheric composition through analyzing ice cores. Basically what they do is they drill deep, deep down into the glaciers in Antarctica, and as the snow is falling, they compact it over time, and these air bubbles trap air from the current atmosphere, whatever that may be at the time. And so the ice is like a snapshot in history of what was happening at the time. And what they do is they melt the ice and the bubbles get released, and we analyze the air that comes out of those bubbles. And so what we've seen is that greenhouse gases have actually increased. Not just carbon dioxide, but all of the greenhouse gases. Carbon dioxide, methane, nitrous oxide, right? The big ones. Another thing that we can do is look at the oxygen isotopes that help determine what temperature it was. And so depending on what oxygen isotope is there, we can see if there were cooler temperatures or warmer temperatures. And we do all this through the law of superposition, meaning that the most recent data is towards the top of the glacier, right? Because it's the most recent. The further down in the glacier you are, the farther away it is in time, right? The farther in the past we go. And so just looking at more of figuring out temperatures and such, more exact as we actually look at sediments, ocean sediments, and you have this foraminifera, which are a type of protists. It's actually kind of a dated term as protists at this point, but we won't get into that. But basically what they are, they're these tiny little marine organisms. They have very hard shells that don't decay, or at least resist decay. And so they get buried over time. And you can see at the core on the right there are these layers, these strata. And we can analyze what species are present. And so as you all know, different species have different range of tolerances. And so we'll see different species at different temperatures. And so with a buildup of shells over millions and millions of years, we can actually determine what the historical temperatures were. And so we put all of this together and we get a pretty good look at what has been happening. And so this graph is 400,000 years, but it's still pretty good, if I do say so myself, right? So you can see you have oxygen isotopes available. We're looking at methane in green there, temperature in red, carbon dioxide at the top. And so what you're able to see is really the different greenhouse gases, like I said, carbon dioxide and methane. Look at the temperatures and the oxygen isotopes that are available or that were present at the time. And we're able to really look at this temperature greenhouse gas correlation. When temperature is up, so are carbon dioxide and methane. When those levels are down, so is the temperature. And so, Earth has been through these warming and cooling periods. We all know about the ice ages, right? And so they do exist, and there are warming periods that do exist. However, now at current time, you can see that it's actually never been higher. So what are our effects of this, warming of this 1 degree? And so, like I said before, right, the polar regions are changing super, super fast. Well, they're changing fast because their temperatures are higher than the rest of the earth, right? They have changed the most. And the reason why, right, is because the ice and snow is melting. And so you have this positive feedback loop. Ice and snow have a high albedo, which reflects sunlight instead of absorbing it. And so when that ice and snow is melting and you have soil which is exposed, that soil has a very low albedo and actually absorbs more heat. And so it warms the ice and snow more, which melts it more, which absorbs more heat, which melts it more, and on and on and on it goes, right? And so at the polar regions, we've actually had a 3 degrees Celsius increase. So quite different than the 1 degree that's average along the entire globe, right? And so it's quite significant. And beyond that positive feedback loop and the melting of the ice and snow, you have species that depend on ice for food and habitat. So you have polar bears and walruses. Narwhals actually use them to escape predators, to like hide up in the ice cracks. Caribou, which use them as important migrating areas, or they use them for ice for migration. And so these species that depend on the ice are really hurting. Not to mention the ice melting is also the permafrost. So the permafrost is this permanently frozen land, and so that's melting, and what's actually inside of the permafrost is a lot of methane. And so again, we have another positive feedback loop. We have warming of the permafrost, methane is released, more warming, more methane, more warming, more methane, and on it goes. Also, very important are the effects that this warming is having on the wind. And so as we know, the Hadley cell, which is really at the girdle of the earth, right along the equator from 0 to 30, it's actually past 30. It's expanding. You have this expanding tropics, and what it's doing is it's pushing those deserts north. If you do remember, right, that descending air at 30 degrees gives us our deserts. You have really dry air, and what's happening is that Hadley cell is expanding, and so that descending air is actually pushing more north than it usually was. Also, we have our jet stream, which is wavering, so it kind of gets all wobbly, and what you end up with is extreme cold spells up really in the northeast. As we know, we've had nor'easters before. You have that polar air coming down into an area that it doesn't usually. And then also you have a lot of dry spells where, like in the west coast, on the west coast of the United States, you have a lot of dry spells from this as well. Thermohaline circulation is starting to change. It's actually slowing. So just to recount what the thermohaline circulation is when you have ice at the polar region, at the Arctic, and that ice is freezing, leaving salt behind in the ocean water, and so you have really salty, really cold water that ends up descending in the ocean and causing this conveyor belt. And as we know, this conveyor belt, this thermohaline circulation, is so important to heat distribution around the world. And so it's actually starting to slow down because that ice is not forming and that ice is melting. And so it's not as salty and it's not as cold. And so that circulation is starting to slow down, thus changing the distribution of heat. And so it can bring us hotter summers, and colder winters in different parts of the world. You have more rainfall because the heat is kind of sitting there. Warmer temperatures actually can hold more moisture, and so we'll have more rainfall. And also, because warm water is building up and not moving as fast, we may have increased extreme events like hurricanes. And so, it's slowing now, but if it slows down more, things could get a lot harder. So some other effects, right? The soil is drying out because you have warmer air, and so you have drought, and it's causing desertification. The soil that has moisture in it, right, that evaporation is increasing because the air is warmer. Also, if there's increased rainfall in an area, you also have increased erosion. Also, our disease vectors are shifting north, so mosquitoes and all kinds of organisms that need warm weather to really thrive, tick-borne illness and all of that good stuff. Not good stuff, bad stuff, right? That range is actually shifting north because it's warmer, and so those vectors of disease are spreading as well, and so therefore increasing the incidence of, in this picture, is Lyme's disease, but other things like malaria, West Nile virus, all of those kinds of vector-borne illness. All right, another effect of this warming climate is also ocean warming. So if the air is warm, it warms the ocean. Remember, water has a very high heat capacity. So although it takes a long time for it to absorb that heat, it does absorb the heat and it holds on to it. And so, problem with this is that a lot of organisms are relying on environmental clues for reproduction. So the change in water temperature, a change in season triggers them to start going through certain reproductive cycles. And so their reproduction are getting kind of messed up. Also, with warmer temperatures, metabolism tends to increase. So, the oxygen levels go down with warmer temperatures, and then respiration increases, and it just takes a lot more to actually, keep your body going. And so certain organisms are having problem with increased metabolism. It just takes more energy. Corals are having a huge problem. When they're stressed out, they expel their zooxanthellae, their symbiotic algae. And so if that stress goes away, they do take them back in. But when you have this constant stressor that never really goes away, that algae stays out and the coral gets bleached, and at some point they can die because they actually do need these algae. And with that comes habitat loss. Corals are, right, the rainforest of the sea, or whatever you want to call it, right? There's so much biodiversity on a coral reef. When those corals die, we get a lot of habitat loss. Another effect of ocean warming is sea level rise. So sea level rise is actually caused by two things. A third of it is through glacial melt. So the land ice in the Arctic is melting, and that water that was frozen on land is now going into the ocean and causing sea level to rise. But that's only a third of the reason why sea level is rising. There's actually something called thermal expansion. And so the water molecules are actually expanding as it warms, and that's causing 2/3 of what we see in sea level rise. It's actually the major cause of sea level rise. And so sea level has changed quite a bit depending on where you are. Again, right? We're looking at average sea level rise. And so this has a huge problem. Just thinking about environmentally, it changes the amount of light that actually gets into the deep water. So, the amount of, or the area that actually would get light, even in the deep ocean, would shift because now the levels are deeper, and so the light doesn't travel as far. It can create new habitat. So, right, your intertidal zone is actually shifted and expanded. Right, with the flooding of area that was dry land before. And then also, in the same respect, you have that loss of habitat of those coastal communities, not just animals, right? You also have people. The majority of the world actually lives in coastal communities. And so that has a huge effect. We have climate refugees all around the world now, especially in island nations. You're seeing a lot of land and freshwater loss in these coastal communities in humans. So another thing that's happening with this increase of greenhouse effect or increase in greenhouse gases is ocean acidification. And so naturally carbon dioxide is going to dissolve into water just like any gas, right? And so carbon dioxide and water together gives us carbonic acid. And that carbonic acid disassociates and we get bicarbonate and then carbonate. And so that carbonate's really, really important for certain marine species. They take up that carbonate, combine it with calcium, and you get calcium carbonate. It builds the skeletons and the shells for a lot of marine organisms, such as, oysters, clams, right? Lots of bivalves, but also sea urchins and corals, right? All made out of calcium carbonate. The problem is that when there is an excess of hydrogen ions, right, which means more hydrogen ions means more acidic or lower pH. And so when those hydrogen atoms are actually in excess, meaning there's a lot more of them, the carbonate is actually more likely to go back to bicarbonate instead of combining with calcium. And so those organisms are not able to get that carbonate because it's not available to them. And so that's a problem. So that, oh, see, I already said that. I should have been on this slide. Anyway, right, so what's happening is that the carbonate is not available, and so they don't have it for uptake, and they can't take it up, and they can't make that calcium carbonate. And so it actually takes them more energy to build their shells, and so their structures can be affected. Their metabolism is, right, they need more energy to actually make them in the first place, and so that can really do some serious harm. And so what do we do about all this? Well, here is a piece of legislation that you all are required to know for College Board, is the Kyoto Protocol. And so basically this was something that extended the 1992 Convention on Climate Change and, named after Kyoto, Japan, where it was. And it commits the parties who signed it and ratified it to reduce their greenhouse gas emissions. And really, it actually puts a heavier burden on more developed countries because, right, we are more responsible for it because we are developed, and underdeveloped nations are not as responsible because, right, they're not as developed, and so therefore they haven't emitted as much. And so, we are able to implement that through trade, really like carbon emitting units, like a cap and trade, and also through development, clean development, whether that's renewable resources or mitigation strategies or whatever it may be. And so it actually entailed 2 commitment periods from 2008 to 2012, and then again from 2013 to 2020. You can see on the map that the U.S. is actually not part of the Kyoto Protocol. We did not ratify it, and so we are actually not involved in this specific legislation. What we are involved in, though, is Paris Climate Agreement. And so in 2015, you had a bunch of countries that came together, 196 in fact, that agreed to try and limit global warming to well below 2 degrees Celsius, preferably not to go above 1.5. We're getting close there. But what's different about this is it actually it requires not only technology, but also economic and social change as well. And so each country submits what they call NDCs, or national determined contributions. And in these plans, they need to communicate not only how they're going to reduce their greenhouse emissions, but also how to build resilience and adapt to these impacts, like I said, both socially and economically, of these rising temperatures. And so, like I have said in class, we signed it in one administration, then we came out of it during another administration, and now we're back in it again. So, this legislation all really depends on who's in charge. And, but we have made a commitment, and we'll see where we go.